In the first session, we were put into our group and explained our project briefing. Our objective for this 2.5-week-long project was to design a payload circuit which included sensors, microprocessor, and a data storage that would collect specific data for the rocket such as acceleration, altitude, time of flight, or temperature. In the first session, we discussed potential ideas, but due to the lack of significant time, we concluded that it was best for each member to go home and research ideas for a brainstorming session. We then met to share findings and assign roles to each member based on strengths and areas of interest, using this Gantt chart that helped with the visualization of the project schedule. Finally, we decided that it would be useful to create a quick MATLAB simulation using some estimated values to get an idea of the motion graphs that we were aiming for and the orders of magnitude that we would be working with dynamics-wise. For the theory and calculations of the motion of the rocket, we started by measuring some parameters of the experiment, such as the radius of the cap, the radius of the bottle, the initial height of the water inside the bottle, the mass of the 3D printed rocket attachments, the empty bottle, and the payload electronics. For the calculations, we tried incorporating Torricelli's law for fluids in a tank into the equation for volumetric flow rate, taking into account the variations with respect to time of both and multiplying by the density of water to get mass flow rate. Then, deriving the total resistive force as the sum of drag force plus deceleration due to gravity, both of which depended on time, and using the fact that net force is equal to the mass times the acceleration to get the velocity equation with respect to time. This nonlinear ODE, however, proved unsolvable using numerical methods, so we decided to change the approach.
Equation 1 shows the energy stored in the water as potential energy. The function of water density on pressure can be modelled as equation 3. The values for compressibility of water remain constant throughout relevant pressures, so we can treat gamma to be constant. Then, including the compressibility of water in our calculations, we can substitute into equation 3 to give equations 4. By substituting equations 4 into equation 1, we get equation 5. Then by evaluating the integral, this gives equation 6. In order to further simplify to meet the desired function equation 7, we neglect the third and higher order terms, and by expanding and further computing the Taylor series of equation 6, this yields a simplified expression with an error of approximately 3%. And finally, by substituting the values in for gamma, V0, and P, we can calculate the potential energy stored in the water rocket system as 365.4 joules. Then, by introducing the gravitational potential energy equation and by assuming energy conservation, we can calculate the maximum height as 37.2 meters.
So for simulations, we used primarily MATLAB to help us understand first how a rocket system differs from other systems. We compared it to a simple pendulum system, which we thought it was easier to help us understand the foundational differences between them. We understood the important factors that stand out from in rocket systems, and those are thrust, drag, mass change, post-rocket propulsion. So as we see in the path simulation of the water rocket propulsion, we see that there is a projectile motion, unlike a simple pendulum system, which is a simple harmonic motion. And using this knowledge, we created various diagrams, such as illustrating the rocket thrust change over time. And then we later found out, we later then illustrated how acceleration changes over time of the rocket, and this closely relates to the thrust force which happens in less than 1 second.
All components used has a VCC and a ground pin. As we have chosen all the components with a built-in voltage regulator, VCC pin can be connected directly to the 5 volts pin on the micro through the breadboard. Ground pins are grounded. For the pressure sensor, Adafruit MMA8451, and the pressure and temperature sensor, DF robot, the SCL pin is connected to pin number 3, and the SDA pin is connected to pin 2 on the microboard. For the Bluetooth connection, to set up the transmit pin on the module is connected to the receive pin on the micro, and the receive pin on the micro is linked to the transmit pin on the module. The connections requires an external power source due to a conflict between cable connections and the pins. Finally, an SD card reader is connected to the micro. MISO, MOSI, and SCK pins are connected to designated pin on the micro, while the SS pin is connected to pin number 7 on the board.
Initially, our group's plan was to include an audible indicator as the additional feature for the rocket. It was clear that the priority was to ensure the temperature and the acceleration measures were all correct. At one point in our project, we tried using a buzzer to create this indicator. Unfortunately, we were unable to get this to work as it was difficult to find the right threshold to use in order to activate the sound from the buzzer at the correct time. Since the time to complete this project was limited, we used the remaining time to focus on the parachute and on other sections of the rocket.
When coding with the Arduino Micro, it was very important to be careful of the pin numbers, and for this we used a pinout diagram of the Arduino Micro, and we also had to use suitable libraries, which could be found online. The approach that we took to coding was using the relevant libraries for the sensors we had, studying the examples and combining this all together to create a complete system. We used the BMP280 Adafruit sensor to sense temperature and pressure. We used the MMA8451 accelerometer to measure position and orientation. To read the sense data into a file, we used an SD card, and we downloaded an SD card library to read the sense data into the file.
Finally, once the completed payload electronics that we put into the rocket were assembled, some remote testing was performed before meeting on test day to assemble and launch the rocket. And after 2.5 weeks of work, we watched our rocket lift off, partially deploy its parachute, and land at a velocity that, although resulted in a cracked nose, left the payload intact and ready to be analyzed. From the experiment, we gathered data for parameters such as acceleration in 3 axes and temperature, pressure, and altitude with respect to time, and we decided to do an XYZ 3D acceleration plot, a pressure over time plot, and a surface plot with interpolation. These graphs were not exactly as predicted in our simulations due to factors such as wind and other drag resistances, which could have improved if it was to be done again. There are also potential improvements for the electronics mentioned in further detail in the report.